Hello and welcome back to High Peak Education. I would like to perform an intuition video about magnetism and electric current. So let's take a look at an experiment that was first done by Hans Christian Ørsted. He was trying to show in 1819 that there was no link between electricity and magnetism. But it turns out that in this classroom setting, it was able to be demonstrated. There's all kinds of legends that a student came up after class and so on. But in any case, it's Hans Christian Ørsted that kind of solidified this. Well, here's the idea. Suppose we have a copper wire moving through some plane, and we call up in this diagram to the north. Well, these compasses, we can change the radius of them, and what we can do is we can change the direction of the electric current. And you'll notice that when we increase the electric current is a lot like a moving charge. It's really just a string of moving charges. So that should produce its own magnetism. And as a result, that should produce a magnetic field. Now it turns out the geometry is that when the conventional current is moving upward, we point our thumb in the direction that the electric current moves of our right hand, and the direction that our fingers sweep is the direction of the magnetic field. So let's see what happens when we do that. So look, the electric current is upward, and then we get that magnetic field that, as viewed from above, looks like it's going counterclockwise. That's the direction that the right-hand rule tells us. Notice that if we increase the radius, there's still a magnetic field, and notice that the radius increasing decreases the strength of the magnetic field. That cannot easily be shown just with compass needles. But it turns out that what we realize is that these magnetic field lines form concentric circles around a straight current carrying wire. That they're not just closed loops, but they are in fact circles with a common center. Well, if the electric current is not downward, if it's not upward, I should say, then the magnetic field is dominated by Earth's magnetic field. But if we do reverse the direction of the electric current to downward, notice that the compass needles go in the exact opposite direction. That is, we point our thumb downward and our fingers rotate like so. So the compass needles are showing the direction of the magnetic field tangent to points of this circle. So each of these red arrows you could think of as magnetic field vectors locally at each of these points. And the direction of the circulation of the magnetic field is clockwise as viewed from above. Let's now look at another example where we have an electric current inside an existing magnetic field. So what I have here is I have a DC, that is a direct current, electric circuit that I can allow current to flow, and also we have a strong magnet, that is a horseshoe magnet. Now remember, this horseshoe magnet should have magnetic field lines coming out of north into south, okay? And then the magnetic field lines should be between south and north in between. And it should be very strong where this wire exists. So here's the deal. If a electric current produces a magnetic field, it should make sense to you that an electric current in an existing magnetic field should experience a magnetic force. So this is basically sort of a restatement of Newton's third law. So if we have the electric current go this direction when we close the switch, you'll see that the electric current goes like so, and the magnetic force is down. Let's see if we can work out why that is. So the electric current is in one direction, and then the magnetic field is in the other direction, and then the thumb points perpendicular to both of them. If we reverse the direction of the electric current, then the magnetic force is in the opposite direction. So again, it's I cross B is the direction of the magnetic force. Okay? So that's basically the idea. Now, by the way, if you get the wrong direction, maybe that you're not looking at the direction of the conventional current. Remember, the direction of conventional current is the direction that positive charges are moving. So in even some of these simulations I'll be showing here today, sometimes we're actually looking at electrons. In fact, some of you may just have realized there was probably a subtlety in what I was doing. I think the magnetic field should be from south to north in the middle here. And if the conventional current is this way, south to north, you would expect the thumb to point upward. But that's because probably this current that's being labeled is the current of electrons, that is the stream of negative charges. And so as a result, perhaps, the conventional current, that's the flow of positive charge, would be this way, and the magnetic field would be this way, and then the thumb would point down. And that's exactly correct. So just be careful on your signs and your directions. Use positive charges, use magnetic field pointing towards north poles, and then, basically that's which should give you the direction of the right-hand rule of magnetic force coming from a string of moving charges in a magnetic field. Let's have a look at another example here. So here's that example I was telling you about in terms of having a think about how moving charges that are negative charges are going to affect a magnetic field nearby. So what we have here is we have a battery, and we have current running in this battery, and then the current is oriented in loops. Notice that if we have a large voltage, we have a large current. If we have a smaller voltage, we have a smaller electric current. Now, by the way, part of the reason I decreased the voltage here to see a smaller value of current is because I want to see what the direction of these moving charges are. Now, if these moving charges are electrons, that's going to be the opposite direction of positive charges moving. Okay, so just be careful with that. But it looks like the electrons are moving, if I'm careful, if I view from the right-hand side, it looks like they're moving clockwise. So what that would mean is positive charges would be moving counterclockwise. So notice what's going to be the direction of the magnetic field. Well, if negative charges are moving clockwise, again, that would be positive charges moving counterclockwise. So positive charges moving counterclockwise as viewed from the right, we rotate our fingers in the direction that the coils go with positive charges, that's counterclockwise as viewed from the right-hand side, and the thumb points to the right. That is to say, the thumb points this way. And that is the magnetic field should be, over here, should be to the right. And that's exactly what we see. So be careful with these positive versus negative charges. Notice that when we get closer to this group of coils and moving charge, the magnetic field is indeed stronger. Remember, the units here are Gauss. And remember, 1 Gauss is 10 to the minus 4 Teslas. Even though Teslas is the SI unit, 1 Tesla is a very strong, large amount of magnetic field. Well, if we increase the voltage, you see that the magnetic field is in the same direction, but notice that the colors get more bright, and that's because there's stronger magnetic field near this group of coils. Also note that if you look at this magnetic field meter, that indeed the magnetic field is stronger in terms of Gauss. And then you may ask, how does the number of loops affect the magnetic field? Well, this little sim only allows us to go up to 4 loops. If we decrease the number of loops, you'll see that the magnetic field is getting weaker. That is to say, if there's fewer turns or fewer coils, there's less enhancement of a magnetic field in the direction that you're looking for. Because, remember, another way to perform the right-hand rule is right-hand rule 2, where you rotate your fingers in the direction that the conventional or positive current goes. The thumb points in the direction of the magnetic field. So if you just have many coils, you just multiply by capital N being an integer, and the magnetic field is stronger and more uniform in the center of those coils. So again, increase the number of coils, stronger magnetic field. By the way, this is called an electromagnet. Electricity that's producing magnetism. Notice that electromagnets are sometimes used to create very strong magnets. I mean, junkyard magnets are often electromagnets. You have a very tightly wound coil and the magnet is strong enough to actually pick up a car. Electromagnets are often used in particle physics experiments when we need to create a very strong magnetic field, and there's many applications of electromagnets. You may ask, how can we reverse the direction of the magnetic field? Well, I think we have to change the direction of the current. So we could change this battery polarity from the positive terminal being on the right-hand side, negative terminal being on the left-hand side, to the positive terminal being on the left-hand side and the negative terminal being on the right-hand side. And you notice that we indeed changed the direction of the magnetic field. The magnitude, that is the size or strength of the magnetic field, didn't change, but the direction did. Now, by the way, you may ask, well, isn't there a type of current, and for that matter voltage, out there where we are constantly changing voltage from positive to negative and positive to negative? And it turns out there is. And that would be alternating current. Notice that alternating current constantly changes the magnetic field direction. And you may ask, why is this useful? It's because we can transmit energy from one coil to the next through air. Now, this is kind of an amazing thing. And that's because if we had another coil nearby, we'd be able to induce another magnetic field on that nearby coil. But there'd be no way to induce that if we didn't have the magnetic field changing in time. So this will be the subject of the next chapter. But suffice it to say, direct current is not going to allow us to change magnetic field through air and with some period of time. Notice that we can change various things about the AC source here. If I increase the amplitude, notice that we have now stronger magnetic fields. Okay, that's because we have more voltage. And if we change the frequency, so in other words, if it's more frequent, there's even stronger magnetic fields, but also the magnetic field changes more rapidly. So this would be, this would be smaller frequency right down here. So changing less often in time. And then this would be weaker amplitude. So not as large of a maximum voltage. Now, by the way, hopefully many of you know that alternating current is the name of the game as it comes to worldwide electrical transmission. And there's a couple reasons. Number one, we can transmit energy through air from one coil to the next. I'll discuss that in a later video. Secondly, with alternating current, unlike direct current, we don't need small booster stations every so often to maintain that nice constant current, because there are always power losses due to resistance. Now, even alternating current has power losses. But with alternating current, the idea is that electric generators tend to produce alternating current. And that's a very useful thing, to actually just put alternating current right out onto the grid directly. By the way, if a user, let's say for a laptop or a hairdryer or something, needs direct current, alternating current can be converted to direct current. But it's a lot harder to convert the other way around, from direct current to alternating current. Okay, so let's look at even another example to make sure you understand the relationship between magnetism and electric current. So what I have here is I have two wires which both carry electric current in the same direction. Furthermore, they are separated by a distance A, and they both have length L, and we're interested in what the magnetic force is between these two wires. Now, typically the equation of showing the magnetic force between these wires is calculated as a force per unit length. But here we're just showing a force. Let's assume we have a certain length. Let's just call it 1 meter. Well, if both wires have their electric current in the same direction, that is, the current runs parallel, the current, let's say in this case, is 2 amperes. If the current of one of the wires gets larger, notice the magnetic force between the wires gets larger. If the current on the other wire gets larger, the magnetic force also gets larger, but if both get larger, the force is quite large. Notice that one or the other or both will increase the magnetic force between the wires. If one of the wires does not carry any electric current, there will be no magnetic force between the wires. Now, you may ask, what's going on? Well, what's going on is each wire is producing its own magnetic field. We discussed that a couple minutes ago from the experiment of Oersted. Also notice that when we have magnetic field impinging upon something that carries electric current, or just carries moving charge, we should have a magnetic force. So, from wire 2, if we point our thumb in the direction of the current of wire 2, the fingers would rotate such that the magnetic field is out of the page at wire 1. But we should perform the vector cross product of the magnetic force, the electric current with the magnetic field in order to calculate the magnetic force direction. So we should take I, and then we know that the magnetic field is, let's see, out of the page. So we should rotate our fingers to be out of the page, and the magnetic force is indeed toward wire 2. Now, by the way, you can work out the same sort of thing at the location of wire 2. The magnetic field would be into the page, the current is that way, and the magnetic force would be up. In other words, when two wires have currents going in the same direction, they have forces between one another that pinch. So this is sometimes called the pinching effect, and this is due to basically Newton's third law, that the force on one on the other is equal to the force of the other on the one in terms of magnitude, but in opposite directions. Now, by the way, what if the two wires have current that goes in the opposite direction of each other? Well, they should repel each other. So parallel wires have magnetic forces that attract in terms of magnetic forces, in terms of that the currents are electric current is parallel to each other, but electric current that's in the opposite direction of one another, that is anti-parallel, should have repulsive forces between these wires. Okay, let's have a look at even another example, and this time let's look at these electric currents in loops, and let's put them in strong magnets and see if we can understand the motor effect. So what I have shown here is a simulation which should help us understand electric motors and the motor effect. What we have is we have a magnetic field, which is shown here in blue, that's B. We also have an area vector of a loop. Now, by the way, we're viewing this loop sort of on edge. And then we have the resulting magnetic forces on each end of this loop. Notice that as viewed from above, the electric current should be going counterclockwise. That is, when viewed on edge, the electric current on the right-hand side goes into the page, and the electric current coming out of the page right here is, again, the response part on the left-hand side of the current loop, which has electric current going counterclockwise. Notice that I can also change the initial angle orientation between the area vector and the magnetic field vector. Now notice, when the area vector is exactly in the opposite direction of the magnetic field, if I want to start this electric motor, nothing's going to happen. Notice that we have a pretty strong electric current that's half an ampere, so that's 500 milliamperes, and a very strong magnetic field of 0.5 teslas. But because of the initial angle, we're not going to get any torque. Why is that? Because this magnetic force at point 4 and at point 2 are both straight in the direction of the loop, and that's not going to produce any torque. In fact, these two forces should cancel one another if they had the same distance away from this magnetic field. So let's stop, and let's now go to what if the area vector is parallel to the magnetic field? Well, same story in terms of result, no motor effect, but that's because the forces are outward from the loop, not inward in this case. Now, by the way, you may wonder, how do you get those forces? Well, you can imagine that if you take the electric current and the local magnetic field and you perform the cross product, you should get the direction of the magnetic force. So if this electric current is out of the page, you point your fingers out of the page, the magnetic field is to the right, the thumb points up. This electric current is into the page, but the magnetic field is to the right, so the magnetic force is downward. So that's how we work out the directions of those forces. But then, here's where things get more interesting. What if we started an angle of, let's say, I don't know, about 45 degrees? 45-degree angle between the magnetic field and the area vector. Notice, look at this. Now it looks like, if this is the axis of rotation, that this force should be, that's like R cross F, there should be a torque that's into the page. That's clockwise. And then how about this other one at the bottom? Well, that's going to be R cross F, also into the page, so there should be a torque on this current loop that's clockwise. Now here's an interesting thing. When we start this, notice that there's a clockwise torque that we typically term as negative, but notice it overshoots, and then we get a counterclockwise torque. And that counterclockwise torque should have the same magnitude, but the opposite direction of rotation after the loop reaches an angle of 45 degrees, but the area vector on the other side of the magnetic field vector. So it turns out that loops that are built where motors are not running properly, the loops just flop back and forth. Now, over time, those loops typically actually slow down, and that's because of friction effects or the fact that we actually might run out of energy from the voltage source. But in any case, the idea is that the motor effect here is due to alternating clockwise versus counterclockwise torques due to the torques on these current loops when there's a uniform magnetic field. Now let me reset this. And let's say, what if the direction is exactly perpendicular between the area vector and the magnetic field? Well, I think we're going to get the maximum amount of torque. So in this case, it'll be clockwise to start once again. That's a negative torque. Notice that we're going to have quite a large torque taking us around in the clockwise direction. But notice by the time we get to the exact opposite position, we'll have a counterclockwise torque, which will take us back. So this is just a very nice starting position for this loop, but the idea is that even though we're getting a pretty large motor effect here, it's still flopping around back and forth. Now, by the way, when people usually talk about the motor effect, which is current loops, so loops with electric current, inside magnetic fields, and they're able to rotate, they mean that the rotation continues to occur in the same direction. So let's in fact stop, and let's now put on alternating current. So what that means is every half turn, we should change the direction of the current, and then we can keep the loop always rotating in the clockwise fashion. Look at that. Did you see how the current changed direction? Look at this. And the current right now is going to change direction again. And then another half turn. Right now, it's going to change direction. And then another half turn. Right now, it's going to change direction. Now, this thing is going to continue to torque, have a net torque, and have a positive net angular acceleration. But the question is, what's going to stop this? Well, there's really nothing limiting this except for, in some sense, the energy source running out, and then the friction on the axle, and then the fact that the alternating current frequency might not be exactly perfectly attuned to how quickly this loop rotates. So you obviously need to perform some careful calculations if you want to do this in practice. By the way, let's take a look at this effect if we have a larger electric current. So look at that. The forces are larger. And also, did you notice that the area vector got larger? The area vector is still in the same direction, but the area vector is closely related to this sort of magnetic dipole moment of loops. So if we start this, notice that in comparison to what we had before, we still have clockwise rotation and clockwise torque, but notice that I didn't turn on the alternating part here. So let me stop and reset. Let me go back to 90 degrees for the initial angle. And then let me make this 1 ampere and alternating current. So every half turn, we should continue the rotation in the clockwise direction. So look at that. The current changed direction. It alternated every half turn. And it turns out this is even a larger angular acceleration than the last experiment that we had alternating current. And then lastly, if you want to make this even larger, you want to go alternating as large a current as possible and as large of a magnetic field as possible. And this should be an enormously angularly accelerating current loop. Now, by the way, you may wonder, at what kind of frequency do we want to do these loops? Well, every country has chosen this, especially if this is something like an electric generator or an electric motor. Okay? So it turns out that in the United States, it's about 60 times per second, 60 hertz. In Europe, it's about 50 hertz. That is 50 cycles per second. Okay? So that's something to keep in mind, that people have to choose these frequencies. Someone has to come up with a standard. Now let's examine this motor effect in a more practical looking motor situation. So what I have here is I have a direct current electric motor, but notice that this direct current electric motor also has something very clever which delivers the electric forces, the magnetic forces to this current loop in a clever way, even though the source here is some DC power source, some voltage that keeps the same polarity. So let's take off the Lorentz forces at first. Notice that hopefully your observation shows that this loop continues to rotate in the same direction, but notice that it has a DC power source, that's direct current. The polarity is not changing, but look at this right here. Every half turn, it seems like the polarity of the direction of the electric current changes on this loop. In fact, the Lorentz force, that's what Professor Walter Fenn calls this, which I am usually just calling the magnetic force. The magnetic force is always in the same direction to cause the torque on this current loop to go in the same direction. As viewed from on end here, it looks like it's going clockwise. So we're always getting clockwise torques here. Okay. By the way, this is shown at about 6 rotations per minute. So 6 RPMs. Notice, let's take a look at those various components. Notice the magnetic field is shown here in blue. That goes out of north into south. Okay. That's the direction of the magnetic field. Okay. And notice that that's the direction of the magnetic field vector. The electric current, we said, should be changing its... So notice that it's not changing its direction in this loop right here from the DC power source. But in the actual loop here, it does change its direction every half turn. Look at that. you'll see that every half turn, the electric current right now, it looks like when viewed from above was, let's see, counterclockwise, but now it's clockwise, and then so on, okay? So notice that since the electric current changes direction, in practice what we have here is either something that we call a commutator, or slip rings, or brushes. So there's some method, some clever way to change the direction of the electric current every half turn. Now, by the way, in practice, you could also just shut off the electric current every half turn. You only get half the amount of torque, but you basically get the idea. Now, if we have the electric current shown and the magnetic force shown, we should be able to understand the direction of the magnetic force. So, electric current, magnetic field, here's the direction of the magnetic force. Let's examine, say, right there. So, the electric current, let's say on the top of the loop, is that way. The magnetic field is down, and then the magnetic force should be to the left. On the bottom, the electric current is back towards that commutator. The magnetic force is, magnetic field is down, so the magnetic force should be to the right. So, there we go. And notice that when we get to a point here where we're about parallel, we switch the direction of the electric current in this loop, and what continues to allow the loop to rotate is basically just a little bit of inertia. Because notice right now there's actually no magnetic forces on the loop. But if we resume, notice that suddenly again, given that the electric current direction in the loop has changed direction, we should have magnetic forces. So we have electric current, magnetic field, and then magnetic force. And that's for the top and the bottom of the loop, producing torque that's counterclockwise. By the way, one thing I also want to say is that we can also change the direction of the way this loop rotates. Notice that if we change the polarity of the DC power source, keep in mind a DC power source here could be like a battery, it's some constant voltage source, you would get the loop to rotate in the opposite direction, clockwise. Notice that also if we increase the rate of rotation, that's going to be because maybe we have a larger DC power source. The rate of rotation is going to increase by either increasing the current, so that's increasing the voltage, increasing the magnetic field, or both. Now, by the way, it turns out that the input energy here is electrical energy. The output here is mechanical energy. So, work is being done. And I should say rotational work, because the input energy is in the form of electrical power, and the output energy is in terms of rotational kinetic energy. Okay? So that's how the transfer of energy is going on here. So this is all I want to say about electric currents and magnetism and motors and the motor effect. Thank you very much for watching this intuition video, and thank you for watching High Peak Education. Please smash that like button if you enjoy this content. Please share this video amongst your social network, as it'll benefit them. I look forward to your comments on this video. Please subscribe to the channel to grow the channel, and I will see you in the next video.